Chair. Good morning, ladies and gentlemen. Thank you for coming. I'm Shijazhuang and I come from China University of Geosciences. Here, my presentation title is Three Algorithms of Magnetization in Vector Inversion for magnet data. Here, Dr. Shijazhuang is my PhD advisor, and the last two authors are my university partners. Okay, thank you. As we know, the typical inversion for magnet data is to invert the distributions of susceptibility, and the direction of magnetization is assumed to lie in the geomagnetic field, but the remanent magnetization and the self-demagnetization of high-susceptibility will change the direction and the intensity of the total magnetization vector. So it's meaningful to recover the distribution of the total magnetic vector when the magnetic source have strong remanent magnetization and or the susceptibility of the source is very high. The most common method of magnetization vector inversion is to recover the three orthogonal components of the total magnetization vector. Because we simplify this method as 3M method. This method is solved the three components in the same equation. This method is used by Dr. Wang and Dr. Peter Nanevri. Besides the magnitude and the inclination and the declination of the total magnetization vector also can represent the total magnetization vector. So the second method is to invert the intensity, inclination, and the declination in this same equation. This method also used by Dr. Peter Nanevri. We call this method as MID. In our research, we propose the third method. We call this method M-ID. As we know, the total field data is sensitivity or is relative to the directions of the magnetization. However, the amplitude anomalies is weakly sensitive to the magnetic direction. For example, this is a statistical model used by Dr. Sherry and Lee. For different inclinations and declinations, their total field data is different, but the amplitude anomalies is similar, and they only include positively values. So the M-ID method, in fact, is a two-step method. The first step, we recover the magnetization intensity from the amplitude data. This method is very common, which has been used by many scholars, such as this group. Subsequently, after we recover the magnetization intensity distribution, we continue to invert the total field data. There are two methods to get the magnetization direction. The first method is recovered directly in this equation. Besides, we also can estimate the magnetization direction according to the correlations between the observed total field data and the predicted observed total field data. We choose the best correlated directions of the optimal inclination and the declination. So we gave a synthetic model to test the three methods. The synthetic model is composed of three parameters, vertical and different parameters. This is their parameters, including their inclinations and the declinations. This left bottom flat shows the total field data, and this figure shows the amplitude data. This slide shows the inversion result of the first method, 3M method. The first method. The left figure shows the 3D distributions of the magnetization intensity, and the right two figures show the directions of the magnetization direction at a horizontal cross section and the two vertical cross sections. And in general, the inversion rate is acceptable, but we can in aspect the distributions of the magnetization intensity and the convergence of the stability of the convergence. But we carefully look at the direction distribution. We found that the direction inversion rate is unacceptable. For example, the direction distributed vary too much from east to direction and north direction and northeast direction. In fact, there are only one direction, that is east by north 60 degrees. So we think that this is because the geophysical non-uniqueness lead to this problem. This is similarly, this is an inversion result used MID result. And generally speaking, the main problem of this method is that when we perform this method, we should give an appropriate initial model. If the initial model is not well, we can difficultly to get an acceptable result. That's because the magnetization intensity, inclination, and declination, they have different contributions to the magnetological anomaly. So if we solve the equations in the same equations, we will have different weight to the three parameters. Go on. This is the inversion result. Use the third method, M-ID. M-ID show two advantages. Firstly, it is not dependent on the initial model very much of the MID method. Besides, it also show convergence of stability, and the recovered magnetic directions doesn't vary very too much of the 3M method. The main direction of the magnetization is this direction. There is not east direction and north direction. So this method, in fact, is making full use of the amplitude and the phase information of the magnetic data. Last slide, we recover the distributions and the magnetization direction. Besides, we also can estimate an averaged magnetic direction. This mapper is a correlation mapper. The peak of max shows the optimal direction. The estimate direction is 40 degrees and 58. This result is close to the true values. As to this method, we can only get an averaged magnetization direction if the magnetization is if have different magnetic integration or the magnetic susceptibility have non-uniqueness and uniform. This method cannot fit this situation. Now we use a real example. This example is looked at the northwest China. The left figure is the total field data, and the right data is the amplitude data. We test the method only use the third method, M-ID method. Only use this method in the real example. This figure shows the 3D distributions of the magnetization intensity, and this is Zhao logs. The magnetization intensity distributions generally show the distributions of the magnetic outer bodies, and this result also verified by many Zhao. This slide shows the inversion result of the magnetization direction. This is a counter map of the correlation. The peak of the max shows that the optimal inclination is 71 and the declination equals 70. This direction is deflected to downwards 15 degrees and eastward 24 degrees from the Earth's magnetic field. We mainly contribute this result as the result of the magnetization. Now this is the result of a high susceptibility premise. The susceptibility equals 10 SI. For this high susceptibility prime, there are strongly self-demagnetization. This is a really distribution of the internal magnetization intensity and the direction. This is our inversion rate and the estimated direction, and this is the susceptibility distribution. The self-demagnetization bases the magnetization direction upon the 7 degrees, reduce the magnetization intensity and the magnetic anomalies about 7 times. Now I summarized my presentation. We compare 3 methods of magnetization vector inversion, but every method has their own advantages and disadvantages. For 3M method, they have good stability of convergence and prone to be impaired by geophysical uniqueness. For MID method, it highly depends on the initial model, and it needs to give upright coefficient to balance the weight. As MID method, M-ID method, it relies the geophysical uniqueness and also makes full use of the amplitude and free motion of the magnetic anomaly, and the average magnetic inclinations and declinations can be dominant. Lastly, magnetization vector inversion provides an indirect ways to investigate the remanent magnetization and the self-demagnetization. Another magnetic transforms such as analytic signals and normalized source strings also can be used to recover the magnetization distribution in the first step of the M-ID method. That's all my presentation. Thank you very much.